Meet the Fellows event. The first talk of the last session is by Eric Mazumdar from Caltech.
Cool. Yeah, thank you. And so today I'm going to be talking about kind of a line of work on learning in the presence of strategic agents. And I'm going to start really, really high level, and then hopefully I'll get down into some of the details. But I just want to start with this very obvious observation that we're increasingly interacting with learning algorithms, either unknowingly or knowingly every single day. So when we're ordering something on Uber Eats or reading the cartoon on the New Yorker, we're implicitly interacting with some form of a learning algorithm. And I think this just goes to show how these algorithms have just been completely deployed across the real world. But as they're actually implemented in real world settings, they can really struggle. And in particular, they can struggle in the face of strategic behaviors. So this is one of my favorite examples. It's about a phenomenon known as surge clubs, which happens on ride-sharing markets. And so what happens, I'll explain it a little bit, is a group of drivers will all kind of band together on Uber, and they'll go to a certain area of the city, like Beverly Hills, and they'll turn off their apps at the same time. Then the Uber surge pricing algorithm notices that there's been a sudden dip in supply, and they'll start surging the price in that location to attract more drivers there. And then the drivers turn on their apps and collect that higher surge price. So, as a system designer, this is not all what I intended, because these drivers are effectively gaming my algorithm. But I think this just goes to show the types of behaviors that algorithms are faced with when they're deployed into the real world. So, this is the type of problem that I'm interested in, kind of developing algorithms that are robust to these type of strategic behaviors and that can reason in the face of these strategic behaviors. So in today's talk, I'm going to talk about kind of 3 different lines of work, at a very, very high level. And I've kind of aligned them with the 3 main topics that will go on in the Learning in Games semester at Simons. The first is going to be about gradient-based algorithms in continuous games. I'll touch very briefly on some of the implications for multi-agent reinforced learning. And then I'll end on some kind of higher level work, more kind of practical work on learning in the presence of strategic agents. So I'm going to start with gradient-based algorithms in continuous games. And the higher level question I want you to keep in mind here is, what can we say about the convergence of gradient-based learning algorithms in non-convex games, where we lose any types of structure that have been kind of classically been relied on in the learning and games community? And this is kind of a long line of work that I've been doing from my PhD all the way to now with collaborators here at Berkeley and UW. So I'm just going to assume that by now you've seen the definition of Nash equilibria today. And so I'll just kind of give you an idea of the types of results that we get. So what we show using basically dynamical systems and control theory is that in non-convex general sum games, gradient play will almost surely avoid a subset of the Nash equilibria of the game. And basically what we show is that Nash equilibria can be locally just straight up unstable in general sum games, meaning that even if you initialize in an arbitrarily small neighborhood of a Nash equilibrium, you'll still diverge. And that's because we can show that Nash equilibria can have basically the set of initializations from which you'll converge to a Nash equilibrium will just be measure 0 in the joint strategy space. In the context of zero-sum games, we show something a little bit more kind of pleasant, which is that Nash equilibria are generically stable in zero-sum games. And so any non-convergence issues that you get there are basically just the result of poor discretizations. And that's kind of nice because it means that Nash equilibria, you can always get local last iterate convergence by doing some kind of smart discretization tricks, like let's say the proximal point algorithm or optimism. Okay, so the second result is that in non-convex general sum games, agents who basically try and use gradient play can converge to spurious stationary points. And so this means that they could converge to local equilibria, where in the worst case, every agent has a direction in which they'd unilaterally like to deviate to lower their cost, but they can't because of the algorithms that they're using. So we think of these as being kind of pretty undesirable equilibria because they're not necessarily even locally rational. And I just want to point out, this was also shown at the same time in the context of zero-sum games by several people. So, I presented this, and I think it's very important to point out that these issues are not just of purely theoretical interest. And to make it practical, I want to take a step into kind of multi-agent reinforcement learning world. So I don't think anyone here needs a reminder of all the successes of deep reinforcement learning, but in all of these games where DeepMind is playing, let's say StarCraft, and OpenAI is playing Dota 2, if we look under the hood, the algorithms that they're using are multi-agent reinforcement learning algorithms, and in particular, they're policy gradient algorithms. So, we decided to ask a very simple question, which is, do policy gradient works in just even simple continuous action space and state space games? So, we also looked at, general sum linear quadratic games, which if you saw from Kai-King's talk just before, I'll kind of go over what they are. So an LQ game is just the generalization of the LQR problem from kind of classic control theory. And it's, a very simple game. There's a shared discrete time dynamical system. All players have an input to this dynamical system. And then every player has a loss function that they want to minimize, which is quadratic in the state of the system and their own inputs. And then they're going to optimize over the space of linearly parameterized policies. So it's a very simple game in the space of kind of continuous actions and continuous states. And our goal was just to understand what happens if you use policy gradient algorithms in these games. So, we can show these games are non-convex. We can show that all local equilibria for policy gradient algorithms have to be Nash equilibria. But if we use policy gradient algorithms in these games, we see that they converge to kind of very non-trivial behaviors. In particular, they converge to cycles. And I think something that I think really sets this apart from a lot of the work that we have seen during the workshop and the bootcamp is that averaging doesn't work here. You can see that on average, which is this dark line, they don't converge to the Nash equilibria. They converge to something else. And that's just because of the fact that these Nash equilibria are unstable. And in dimension higher than 2, you don't have any guarantees that inside of a limit cycle, you have an equilibrium. So, we showed that this actually happened in kind of a large set of linear quadratic games. In particular, like just by randomly sampling, we saw that this happened in up to 1 in 4 kind of general sum multi-agent games. So, policy gradients might not be the way forward. So, the takeaway from these first 2 parts is that current machine learning algorithms have no guarantees of finding game relevant solutions in continuous games without assuming more structure. And if non-convergence, and I think an interesting question is that if non-convergence isn't a discretization issue, will optimism and proximal methods still work? And then the second question is, for what classes of games can we actually give convergence guarantees? So we saw from Kai-Shing that they can actually give global convergence of policy gradient algorithms in zero-sum games. So that was a really nice result. And then in NeurIPS this year, we were able to show that in classes of non-convex, non-concave zero-sum games, we can actually give last iterate convergence to local min-max equilibria. So equilibria that satisfy certain curvature properties, as long as the 2 players have a certain finite timescale separation. And that's kind of using some interesting kind of Lyapunov theory. Great. And so in the remaining time, I just want to move on to kind of some much more recent work on learning in the presence of strategic agents. And in particular, we'll be looking at the problem of strategic classification. So the question, kind of overarching question here, is how should we learn in strategic classification if strategic agents gradually adapt to our deployed models? So the general setup in strategic classification is that of, you have a decision maker and strategic agents. A decision maker wants to minimize its prediction loss. Strategic agents want a favorable predictions out of this decision maker. And, they'll deploy, the decision maker deploys a model, and then strategic agents, will respond. So in particular, strategic agents and decision makers will adapt to each other's actions. So, we ask the question, what happens if this is repeated over and over and over time? And in particular, if we, unroll time and we allow agents and the decision maker to update, at perhaps different timescales. So what will happen if they're both adapting to each other over time, over different timescales? And I want to point out that the vast majority of past work in strategic classification always models agents as playing an instantaneous best response. So not gradually adapting over time, but always optimally adapting. So this is kind of the main difference in our model. And so, we kind of make this observation that increasingly now, because decision makers are, tech companies who are deploying algorithms, they can often choose how fast they learn relative to the population of users. So in particular, a decision maker can be much, much slower relative to the agents, or much, much faster relative to the agents. And at a high level, what we show is that if agents are basically no regret learners, then these two scenarios, where the decision maker is fast or where the decision maker is slow, will lead to drastically different game theoretic equilibria. In particular, they'll lead to different stackable equilibria of the underlying game, one where the decision maker leads and the other one where the decision maker follows. And so really the takeaway here is that the relative learning rate can be used to select for specific Stackelberg equilibria and strategic classification. So at a high level, the takeaway is just that when you're learning in the presence of adaptive, no regret strategic agents, the learning rate doesn't only affect the speed of convergence to a solution, it actually also affects the type of solution that you converge to. I think that's a really important point to hammer home. And so, moving forward, I think that there's this really interesting question, which is what other benign design choices are we making when we are deploying algorithms that actually affect performance in competitive settings? And so, I think I want to wrap up there and just say I'm very excited about, this entire semester here at Simons. And so if you have any questions, I'd be happy to answer them. And thanks for listening.
Questions for me?
I'm just wondering, like for the second part of the talk, when you talk about learning at a faster rate or a slower rate, do we know if the convergence point is a Nash equilibrium? But it may not be a Nash equilibrium.
No, they're not.
They're not.
The next speaker is Anish Agarwal.